Hello, my friends of Qatari Labs. My name is Salome. Welcome to this tutorial. This tutorial will be about the water intake design with OpenFOAM and Salome platform. What we will do, we will use a tool that is called OpenFOAM for Windows. Yeah, OpenFOAM for Windows. Okay, and then we will design water intake from a channel of a specific geometries. So let's see CDD. I will show you what is the result of this. Let's see let's set the tutorial this. Okay, let's set the OpenFOAM. Let's set the. This is where I store. Later on, we are going to recreate the whole process. Okay, so if we say paraFOAM, it will run ParaView. And this is something great about OpenFOAM, because OpenFOAM is actually, OpenFOAM for Windows actually brings the whole capabilities of OpenFOAM in Linux to Windows, because we know that that many people here use Windows. So what we will design, here I say apply. Okay, this is a main channel. This is a trapezoidal channel. And here there is another channel here that is the intake channel. So flow will come from this, and then it will, flow that come from this will, upon the flow, the velocities and so on, will create a specific path, and then a specific flow path here, and some water will diverge in this intake channel. Okay, so here we can see the results. Let's see alpha water. So here we see water at time 1, time 2, let's see, and here you see how water is going through the channel. Okay, and let's see, we have already seen just half a second. Okay, and this is ParaView, because actually ParaView is parallelizing the whole processors of my computer. So then here we will see that some of this water will get into the channel. Okay, so that's what we are going to see, but then that will be in the end of this tutorial. So I just say here, I stop it, and then I close it. Okay, and then I am going to leave it like this, because we are going to use another software that is called Salome platform. Okay, in case that you don't know Salome platform, what is this? Okay, so say Salome platform. Salome platform is actually a tool for developing. It's a tool for developing. It's an open source software as well, but it can make you geometries, and it's really good for CAD, so for computer assisted design. But we just use it to create the mesh for Salome or OpenFOAM. So actually you can download it in Windows, and that is cool because you can work with this. Okay, here is for Windows. Yep, and then Salome is not an actual. It do not have an installation like OpenFOAM, like any other Windows, because actually what you will do is you will download it. For example, here I have software. Here I have Salome, that is just the file that I have downloaded, and in order to run it I have to go to work. So what you will download is something like this, maybe another version, a newer version, and then you just go to work, and then you just type run Salome. Okay, it will ask for some permissions. Okay, Don't worry about the permissions, because just give all the permissions that this software needs. Okay. Okay, it's creating a virtual machine and so on. Okay, what we are Hatari Labs. And what is Hatari Labs? Hatari Labs is a blog that is which main goal is to promote the use of open source software in the evaluation of water resources. Okay, so we have a website, yeah, and our website is kind of it's actually the English version of a Spanish version that is called Gida Hatari, but in English it is called Hatari Labs. Okay. We have a lot of tutorials, mostly in groundwater, but we have also in surface water like this one. And what else? We have, for example, we have a newsletter, so you can sign up for the newsletter here. We have categories. We will have some courses in the future. In the future, there will be some courses, and as well, we will have some webinars. So we will have both of them. Okay. So please follow us on Facebook, and if you like what we give, sign up for this YouTube channel as well. Okay. So this is an invitation to follow Water Labs. But here you will find Salome. Okay. Okay, so we are going to create a new geometry, yeah, new geometry, and this will be pretty, it's really, Salome is really, I mean, I have never had any formal training in Salome, but really the software is really into the user, so it's really easy to do things with Salome with mostly with few with few knowledge. Okay, so here we go to geometry. I'm going to create a point. My first point will be 0, 0, 1.5. Okay, I say apply. My second point will be 0.5, 0, and 0. The third point will be 2.5, 0, and 0. And the third point will be 3, 0, 1.5. Apply. Okay. Then we have another point that will be the other extreme, that will be 0, 11, 1.5. Then will be 0.5, 11, 0. You will see the results of these values later on. Okay. Then we have 2.5, 0. Then you have 3. And then you will have 11, and then you will have 1.5. Okay, what is this? Okay, if I go to here, you will see that we have already the trapezoidal section of the channel here and here. So then what we are going to do is we are going to create a solid. In order to create a solid it's really easy. I mean, yes, I will do it because I don't want this tutorial to be like half an hour, no, maybe 2 hours. So I will do it pretty fast, but in YouTube you can do the pause and then you can do the rewind. I mean, you are freely to stop it whenever you want. So here I just select these ones, and then I will do a curve, and then I will do a wire. So it's a wire, yeah, and it's a closed wire. So I say apply, and then here I say apply, okay, and then here I just select, oops, I'm pressing shift, no, sorry. So here I create this wall, okay, doesn't matter. It really is up to the order of the points. Wow. So yeah, okay, I just go to the top. Why is happening? What is happening? Let's see. Okay, apply. So I have the intake, the outlet, the atmosphere. Here, here, here. Okay, this is this wall, and then something is going on. I mean, you have to play around, okay, because it really depends the order of the points, the how it will appear, how you create the. Let's see. Okay, so it doesn't work in this order. Maybe it works in this order. Okay, apply, apply and close. Okay, so we have created the wires of our. We have created the wires of our channel. So these are the wires. So here, okay, here this is the bottom part. Here is the inlet, the outlet, the top one wall and the other wall. Okay, great. So after that, we have to create the faces, and in order to create the faces, yeah, what we are going to do is we are going to create faces is with this one, and then the first phase will be a planar, because actually there are planar. There are some issues when you do some other geometries, but not here. Okay, and then like I wanted to show you that this is this. Apply and close. Okay. So here I have already the solid that is my channel. And this no, I have some faces. Yeah, and I will select the whole faces because I need to do a shell. Okay. The shell, it will be from these objects. Okay. No, I have to do a shell. I have to do a shell. A shell. This is the shell, and the shell will be from the shell is done from objects. Okay. Apply close, and then I have a shell, and from the shell I have to do it as solid. Okay. The shell, do it as solid, and then I have a solid. Okay. That's great. Here is my solid. It's already a solid. Okay. So I have the main channel. Yep. What else do I need? I need to do another channel. So it's the intake channel. So in order to do the intake channel, I will create 2 points. The first point will be mine. This really depends on your local coordinate. I really strongly recommend that you use local coordinates, because Salome and OpenFOAM is not good when you use geographic coordinates. Okay. That is the first point, apply. And then the next point will be, oops, 1.5, 6, and 1.5. I am close, and that's it. How do you like it? It's great, no? So we can create a box that is a solid in between both of them. So just create a box. From this, point 1 will be this one, point 1. And then here you have created a box, apply and close. And then you have two solid. You have the solid one and the box. Yeah, and you see that they both share some geometric space. So in order to, we can fuse them, yeah, and we need to fuse them. How we need to fuse them? We need to fuse them by using this fuse, okay? So here we have this fuse that is actually the fuse of these two objects, okay? Great. And we say apply and close. And here we put apply and close, and then this is the fuse. This is the fuse from these two objects, okay? That's great. Yep. Then what else we are going to do? Okay, so if we have the fuse of this object, what else we are going to do is we have to create some groups. So we go to, on the fuse, we can save this project, okay? File, save, and where we are going to save it, I use the D drive of my computer, yeah, because my C drive is already full. Yeah, it's up to you, but let's see that we are going to say new folder, tutorial of water intake. Okay, so in the tutorial of the water intake, we are going to create a new folder that will be Salome, and on Salome we will save this. Okay, great, that is great. Okay, what else we are going to do? Okay, we are going to create a group, create groups, and the groups will be located in from faces, okay, and so let's see, this group will be called atmosphere, okay, apply. This will be the inlet, apply, okay, apply. This will be the outlet 2, because there are other outlet 2, apply, apply. This, sorry, where is it? This will be the outlet 3, and this will be the outlet 1, apply. This will be something that is called concrete walls, because this will be of concrete. So this, but not only this as well, and on this side there are many. So it's this, 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 and this, there are 6, okay, and this will be concrete wall. Okay, great. Apply and close. Okay, so if you see, we have created some groups on our geometry. Okay, so here is it, inlet, outlet 2, outlet 1, concrete wall. Okay, that's great. So we are going to do a mesh. So we save it again, and then we go to mesh, and we wait. Okay, I hope that this tutorial will be fine for you, and maybe you have some knowledge on OpenFOAM, or maybe you want, there is on the description of this project, there are some animations, so I strongly recommend to see those animations as well. Yep, because I want that you get a feeling of what we are doing. The process is not so short. Okay, so here we have the fuse, and on the fuse we have we are going to create a mesh. But we select fuse because we create a mesh from the fuse. Yeah, okay, and then here will be the NetGen 1D, 2D, 3G. Okay, and then we get a hypothesis in parameters. And this is very important because for our for our model, we want huge discretization at 0.1, let's see, and the minimum size it will be 0.05, yeah, because otherwise we won't get the resolution to, I mean, the water intake that you are planning to simulate is only have 1 meters depth. So if you don't put if you don't put appropriate number of cells, like you will have very low resolution of how water is going through the intake. Okay, then later on you can do some specific refinements that maybe be of much profit to run this model faster. But in this case, we are going to do a refination for the whole project. Okay, so we create this. We say apply and close, and then we go mesh, and then we say compute. Okay, this mesh is coarse. It's a coarse. Sorry about my English. Okay, so it takes some time to create the mesh. And the mesh will have some values here that I'm going to record. Okay, so what has happened here? Okay, great. So you will be running a mesh of 7,502 edges. It will be 46,043 nodes, and it will be 242,659 exact tetraeders. Okay. So it's tetra. Okay, that's right. So we say close here. And then if you see, voila, you have your mesh. And this mesh is really beautiful. I don't know if there is a beauty contest of meshes, but these ones, if you make it this on your first tutorial of OpenFOAM, congratulations, because you have made a much success here. Okay, later on, what we have here is that we go to view, we go to create groups. Okay, we go to create group. Okay, and then we say on faces and group on geometry, and then I selected the atmosphere, for example. So here I select direct geometry, atmosphere, and this group will be atmosphere. Apply. And then I say inlet, and the group will be as well inlet color because I want. And then I say outlet 2, and this will be outlet 2. And this will be outlet 1, and this will be outlet 1. And then it will be concrete wall, and this will be concrete wall. This will be apply and close. Okay. Cool. Let one, let two, let the atmosphere. Save your project, save your project, save your project. And this mesh, then you are going to file, export, UMV. And this will be mesh 1 UMV, and this will be in Salome. And then we say save. Okay. That is great because you have saved the mesh. Okay. Great. You are doing really great. Okay. Then this is actually the design of the this is something that we will use for the as a how to say this will be a SketchUp or like a draft or like a reference for our model. So here this is already a developed model, okay? So, and it's running just for 4 seconds, not so much, okay? So, because it takes a while to do it. So, in our case, I'm going to, yeah, you will receive, okay? I'm going Control C. I go to this. You will receive these files. Don't worry. Yeah, but yeah, on the description of this video, you will receive this file. Okay. Okay. Yeah, it's a little bit heavy because it's already run, but we have to clean it in order to get the in order to. Okay, so we have here. I'm going to delete the whole. I mean, I will just have the first step. Okay, so here is okay, great. Then on post processing, no, in constant polymesh, this will be as well deleted. Okay, and this mesh is actually from another mesh. I will put the mesh that we have created. Okay, and that's it. That's it. What we are going to have on the description of this video. You will have this data because from this data is the one that we are going to run the model. Okay, so we go to, and then you will receive this. That these are these 2 folders. Okay, okay, sorry. This will be water intake. Yeah, because I don't like to put Spanish names on my English tutorials. Okay. So here, let's see. I have the mesh that I have done. Yep. I have the 0, yeah, that I have to delete this and then I just go, I do a copy here and I paste it, and then I change it to, okay, yeah. Okay, let's see what we have here. So I just apply alpha water and then see in WordPad. And then I see that I have the inlet is actually has a fixed value of 1, so there is water there. Yeah. The concrete wall is 0 gradient. The outlet one is 0 gradient and is 0, so there is no water in neither of the. At the beginning, there is no water there. And the atmosphere is an inlet outlet, so water can go out of the system through the top. Okay. And but it's not with water. Okay. So this is alpha water. So just on the boundary conditions, there is water. Okay, great. So we have some values for the turbulence because this is a runs. This is OpenFOAM with the run, so it's actually a turbulent model. So then you will see some values that define the turbulence. Okay, so it's the K and the omega. Okay, so both are. I strongly recommend that you go through the tutorials, to the documentation, and see what is actually stands for K and what actually stands for omega. Okay, then we go to pressure, and then see the atmosphere has these configurations. The outlet is 0 gradient, so water is just going out of the system, while the rest is a fixed flux pressure. Okay, and then the velocity, because this velocity is actually 10 cubic meters per second. So is a volumetric flow rate. So it's actually volume, it's not mass. So it's 10 cubic meters per second. The water that is going through the system. Okay. Then we have the concrete volume that is actually water is not going out. Atmosphere is actually water. Inlet, outlet, and the outlet are as well inlet, outlet, and those are just taking water out of the system. What does it mean? That water that is arriving to these areas is just getting out. So it's just like a door that takes all the water out, all the water that reaches. Okay, let's go to constant. And then we see that the gravity is actually going down. Then we see some transport properties. We see some values here, the density, but we don't have transport here. And we have some turbulence properties. This is one, and then this is how we have configured the RAS model because we consider turbulent. Okay, on the post-processing, on system, we have the control dict where we are going to run this for it says 10, but I'm going just to say it just for 4. Yeah, otherwise is really it's really I mean, if you parallelize your processors and then if you run it with higher computers and so on, you can run it maybe for 10, 3 minutes, 4 minutes, and so on, and maybe you can do even more with better initial conditions. However, this is just a tutorial, and there is a perception that you have to run OpenFOAM on higher computers, but all my tutorials are done with Core i5. So and this is okay. So it really depends on how do you conceptualize your model. It depends on how fast and how well are you going to construct, and how many computer power will you need? Okay, so it's not really that you need a strong computer to create some good stuff in OpenFOAM. This is not the case. You will create. I mean, if you are a beginner, like, use just a normal processor. Okay. Let's see, delta t, that is okay. Just save it. Okay, these are schemes for the resolution. Okay. Now these are the schemes, and this is the for the resolution, that is the solver that I actually say. And this set field dixing is actually creates the initial conditions and says that it will have, I mean, the channel is not empty, that actually will have 0.3, I mean, like elevation of 0.3 meters. Okay, cool, that's great. So once you have done it, you just go to, like, say, look. Yeah, this is actually in OpenFOAM. It could, when you call, I will call it again. OpenFOAM for Windows. So CDD, because actually, look, I am in D here in D. And so say ls, that is actually there, say the simulation OpenFOAM, then tutorial, water intake, and then water intake, and then, okay, nothing else. Yeah, because I'm just setting this route, this path, the simulation OpenFOAM, tutorial, water intake, okay. Okay, let's, and then here I just to do some steps. So first is ideas UNV mesh 1, because this actually create a mesh. Okay, then what else I need to do? Set fields. Okay, and then what else I need to do? I need to ideas, set fields, and then I need to do check mesh. And then once I have already this, I can do paraFOAM in order to see the initial conditions of the model I have. Okay. So here I will have this, and then if we go to alpha water, we will see that the boundary conditions has water, and then that the channel has 0.3. Okay, I just check this. Okay, and then I put interFOAM, and then it will create, let's see how, then it will give me an error that say, okay, cool, you have done everything right, but there is a patch that has to be wall, and this actually you create this manually. So you go to the water intake, and then say what is say here, then you go to constant, you go to polymesh, and then you go to boundary, then you say edit on notepad, and it says that the concrete wall should be patched, no, should be wall. Yeah, okay, so yes, you just say wall here, then you just save it, and then you say again, okay, and that's it. Yep. The model will run, I think, maybe for 3 or 4 hours. Yeah, because if you see the delta t is pretty slow. Yeah, and I will stop this. I will stop this emission, and then I will see you on the next once we have already when we have the results. So I hope that that you stand for us, and then like you see the second part of this tutorial. Okay. And okay, so see you in the next tutorial. Bye bye.